What is it about quantum field theory that makes it not rigorously defined other than the path integral? Because there are other approaches to quantizing than the path integral.
How much time do we have? So what makes it hard?
Not hard. Not rigorously defined.
Not rigorously defined. So, well, I mean, we have rigorously defined quantum field theories, but they tend to be quantum field theories defined in very low numbers of space-time dimensions, where you can like rigorously define all the integrations and take all the limits. We have quantum field theories defined by what are called the Whiteman axioms, but these axioms are very strong and preclude the kinds of quantum field theories that seem most apt to describe sort of nature. There's so many different angles I could take for this. I'll just pick one. So here's one way to see what can go wrong. If you take quantum electrodynamics, which is the quantum field theory that best describes electrons, and if you want, you can add some of the heavier cousins of electrons like muons, and interacting with photons, with the electromagnetic field. I should say, by the way, that most of what we do when we do quantum field theory is not look at particles dancing around. What we do is we introduce, in the asymptotically distant past, a so-called in-state, a quantum state vector that consists of some menu, some assortment of particles that are supposed to come into the experiment. And then we write down some menu of outgoing particles. You might go, how do we know what particle is going to come out? Well, we don't. We're going to be computing a probability that this goes to that. So we start with some incoming particles. We start with some proposed outgoing particles. And then using either the path integral or other calculational methods, we compute the so-called complex valued scattering amplitude. It's the complex number you get when you put these things together. It's the complex number that when you mod squared is supposed to be connected to the probability you'll get that particular outcome. In practice, what we do is compute what are called scattering cross-sections, which is like what fraction come out one way, what fraction come out another way. Notice these are all phrased in a way that is perfectly consistent with the textbook formulation of quantum mechanics. We're not asking what's going on in between. We're not dealing with macroscopic systems. We're doing exactly what the textbook axioms ask us to do, which is you prepare, you compute probabilities of measurement outcomes. All the averages and numbers you're doing are many, like experiments repeated large numbers of times. So you're not going to run in, for the most part, to any of the fundamental inconsistencies or ambiguities in textbook quantum theory. So it's very easy to do quantum field theory and think there's no problem. Everything is great. We're doing quantum field theory. What's the problem? It's because most of what you're doing just doesn't run into any of those ambiguities you run into with the axioms. Now, this theory is very useful, and we can compute a lot of stuff. We can't compute everything. There's some ingredients that you have to take from experiment, right? The so-called physical couplings you have to go out and measure, and you plug them into the model. Because if you just sort of naively try to compute everything from first principles, what you discover is that certain quantities you might want to compute depend very sensitively on sort of the upper boundary of what you've put on the theory. So when you study a theory like this, you recognize you can't access arbitrarily high energy physics. Our experiments don't pump in more than a certain amount of energy. So we shouldn't extrapolate the theory to arbitrarily high energies. We're going to put a cutoff on the theory. We're only going to discuss what's happening in the theory up to some energy level, some energy cutoff. It's just that some of the things you might want to calculate from first principles depend sensitively on the cutoff, and those are things your theory cannot provide you with. So we have to take some things from empirical data and put them in. We plug them in. They become some of the parameters in our theory. The standard model has about 20 or so of these parameters you have to take from experiment and plug them in. And once you have them, you can now make huge numbers of non-trivial, highly accurate predictions about what happens. But you still have this upper boundary. And if you try to calculate things at arbitrarily high energies, eventually your calculations stop working. So one of the dirty secrets of physics is that much of the calculating we do is highly approximate. A lot of it, when we do it by hand, is using a tool called perturbation theory, which I cover in some of my courses. Perturbation theory is a systematic recipe for calculating things. And this recipe just doesn't work very well once you start trying to push your predictions beyond a certain energy level. There's a trick you can do to change what the theory looks like as you study at different energy levels. It's called renormalization. And what you find is that some of the parameters in the theory, they stop having values that make it possible to do consistent perturbation theory. Now, if you wanted to rigorously define a quantum field theory, what you want to do is take some kind of a limit where you can study the theory at arbitrarily high energies. This corresponds, roughly speaking, to being able to assign degrees of freedom to arbitrarily small points in space. And you see there's immediately an obstruction here. For most of our theories, there's a cutoff. There's a boundary we can't go beyond. The theory simply doesn't let us go to arbitrarily high energy scales. And so we're not going to be able to write down a so-called ultraviolet complete, like perfectly fine-grained version of this theory. We can only use a theory up to some cutoff. The standard model, for example, is not expected to hold to arbitrarily high energy scales. We think that the theory is reliable only up to like a 10 tera electron volt scale. And it's one of the reasons why we're building experiments or trying to build experiments, trying to do experiments to probe the physics that's going on above those scales where the standard model may no longer be making the correct predictions. Right, all of this takes us pretty far, no pun intended, afield of what we were talking about before. But these are the kinds of things like maybe quantum field theories in the real world, real life out there in the wild, quantum field theories are never perfectly defined. Maybe all we have is a cascade of so-called effective field theories that are all well-defined within some bounds. And there is no ultimate theory that is like perfect and fine-grained and, perfectly fine-grained and ultraviolet complete. Maybe there's just like a tower of these theories. This makes questions of ontology and what's physically out there, I think, very murky. Because if we think there's never going to be some fundamental theory at the bottom of all of this, what really is out there in nature? That's, I think, an open question. Whether or not you want to rephrase that question in the language of this sort of indivisible stochastic approach, I don't know. Or it could be that these theories tap out to some ultimate quantum field theory or some very different kind of theory, like string theory or something like that. I mean, there are many proposals for maybe where this terminates. But I don't know. What I will say is this, though. There is a view that nature is fundamentally described by Hilbert spaces in quantum mechanics, the Hilbert space formulation of quantum mechanics. And if that's fundamental, then we already know what nature fundamentally is. Nature fundamentally is some wave function. That's it. Some wave function in some Hilbert space. We don't exactly know the features of the wave function. We don't know whether it's best described in terms of fields or something else, but we already know the fundamental ontology of nature. It's a wave function. So we're good. I think that's too ambitious. In the indivisible stochastic approach, there's no wave function. So the wave function is not what the ontology is. The wave function is whatever your choice of configurations are. And if you're modeling particles, you'll use particle configurations. If you're modeling fields, you'll use field configurations. If there's some ultimate system that grounds everything else, some system at the bottom, some system that if we understood it and understood its laws, we would have the unified theory of all of physics, there would presumably be some configurations for that, and we would use those instead. But we don't know that theory yet. And so I think it's premature to think that we know the right fundamental degrees of freedom. So if someone asks me, what do I think is fundamentally out there? I don't know. But then I'm just where we were 100 years ago or 150 years ago. We don't know the ultimate theory of nature yet. And I think it's premature to, at this point, guess what the ultimate ontology is going to be until we have that theory, should we ever have it.
Well, I'm interested in ultimate theories.
Theory of everything is the name of your podcast. Sorry, I don't have one for you.
Well, I'm interested in your thoughts into how to merge quantum field theory with gravity. So I know we have a slew of audience questions and we're going to get to them, but they're going to have to wait because I have these questions first.
These are like close to what I wanted to also talk about. So go on. Yeah.
Great. Yeah. Okay. So 2 questions here. People say that, okay, look, we have this Heisenberg uncertainty and that applies even in QFTs. And so thus space-time is shaky. Okay. But space-time in QFT is defined. You can perfectly pick out an x, t. And the values of creating particles and the fields themselves vibrate or are uncertain. But the space-time itself is there and given. However, some people say that if you were to zoom in and you follow QFT because of Heisenberg's uncertainty, you thus get to uncertainties of space-time itself. Is that argument valid? Now, I imagine that one of the ways that they get to this argument is by saying you have an energy-time uncertainty. In general relativity, space-time itself has energy, and so thus space-time itself must have some uncertainty to it. But then you could also say, well, in QFT, you don't know if the energy that it's talking about is the same of, okay. if you have a statement that applies to all natural numbers, you can't just say that so x squared is always going to be a natural number if you're pulling from natural numbers. But not every number squared is a natural number. So it depends on the scope of what you're quantifying over. So is it the case that in Q of t we can apply the energy time uncertainty to GR? I don't know. Okay, so that's one question.
We should address that question first before we ask any more questions.
Sure.
Yeah. So it's important to step back here and just make sure we know what we're all talking about. So a quantum field, just because maybe not everyone knows what they are. So in a typical Hilbert space formulation of a quantum system, we have observables. Observables are these self-adjoint operators. And in a quantum field, we have operators associated with all points in space, right? And if we work in a formulation in which we move the time evolution out of the state vectors and into the observables, we have what's called the Heisenberg picture. And then our field operators depend on space and time. It's a fancy way of saying everywhere in space-time, we've got these sort of local operators that are associated with points in space and time. Quantum field theories like QED, we talked about quantum electrodynamics, they presuppose this classical background space-time. There's no gravity. Space-time is usually treated as flat. We call flat ordinary special relativity space-time. We call it Minkowski space-time. You can do quantum field theory in a static curved space-time, still not treating gravity as dynamical, but that gets very complicated. Let's start with quantum field theories like QED on special relativity, flat, non-dynamical space-time. In that case, you're right. X, Y, Z, the coordinates of where you are, and T, do not fluctuate. They are fixed features of the background architecture of space-time. They're the stage on which the action is happening. Your question about the uncertainty principle and about fluctuations of fields is an interesting question. In the Dirac-von Neumann formulation of quantum mechanics, nothing is fluctuating between measurements because nothing is happening between measurements. The only things that are happening are measurements in the Dirac-von Neumann formulation. So to say, oh, when you're not measuring it, the fields are just like dancing, the Dirac-von Neumann axioms don't say that. They say nothing about it. They don't say that particles are zooming around. The Dirac-von Neumann axioms don't let you say, oh, the reason this happened was a photon emitted an electron. All that is for color. I said this in one of our earlier conversations that physicists often talk this way. They're like, oh, this happened because an electron emitted that and did this, and oh, the field was fluctuating. If you're only working on the Dirac-von Neumann axioms, all of that is just fluff. None of it is really legitimated by the axioms. Now, if you're frustrated by that, and you're like, well, but surely something is happening. I want to be able to say something is happening. Well, then you're on my side, which is that we need to do something to the Dirac-von Neumann axioms. You're making my case for me, okay? So the uncertainty principle, the traditional uncertainty principle, we talked about this a little earlier. An observable, corresponds to a certain basis, and when the state vector of your system is aligned with one axis of that basis, you're definitely going to get that result when you measure it. If the state vector is not aligned with that basis vector, it's got components along multiple basis vectors, then you're going to have probabilistic measurement results given by the Born rule. And you can be aligned along the axis of one observable and have a definite result, but not along one axis of another observable, and you don't have a definite result. And if you change the state vector so that it's aligned along the axis of one, it's not aligned along the axis of the other. And this is the uncertainty principle, that some observables will have sharp values that when you measure them, you always get a definite result, and others won't. And if you try to make one observable sharp, others will become unsharp. This is the uncertainty principle. But notice again, this is all phrased at the level of measurements. We're not saying that between measurements, anything is fluctuating. So honestly, there's like no way to really talk about to say that the field is fluctuating on top of a space-time, or to say anything more about the Heisenberg uncertainty principle other than this is the pattern of measurement results we get when we do measurements on the system. Now, if you want to do something like Bohmian mechanics or the indivisible stochastic approach or the many worlds approach or something like that, now we can actually begin to talk about what's happening between measurements, because these are all theories that describe things happening that are not just the narrow class of measurements. In some of the theories, like in the indivisible stochastic approach, there's stochastic behavior. The fields really are fluctuating. In the Bohmian approach, it kind of depends on whether you're trying to get fields into a deterministic kind of Bohmian approach or whether you're going to allow the fields to be stochastic in some sense. There are many different formulations of Bohmian mechanics for fields, and I can't do justice to all of them. Some of them, the fields would be fluctuating. Some of them, the fields wouldn't be. In some of them, you deny that there are fields and try to do everything with particles somehow. Many worlds is a little more subtle, because in many worlds, there's not one reality in which things are fluctuating. It's just more subtle. And we'll talk about the many worlds approach a little bit later.
To stay informed in an ever-evolving landscape, I see The Economist as a wellspring of insightful analysis and in-depth reporting on the various topics we explore here and beyond. The Economist's commitment to rigorous journalism means you get a clear picture of the world's most significant developments, whether it's in scientific innovation or the shifting tectonic plates of global politics. The Economist provides comprehensive coverage that goes beyond the headlines. What sets The Economist apart is their ability to make complex issues accessible and engaging, much like we strive to do in this podcast. If you're passionate about expanding your knowledge and gaining a deeper understanding of the forces that shape our world, then I highly recommend subscribing to The Economist. It's an investment into intellectual growth, one that you won't regret. As a listener of TOE, you get a special 20% off discount. Now you can enjoy The Economist and all it has to offer for less. Head over to their website, www.economist.com/TOE, TOE, to get started. Thanks for tuning in, and now back to our explorations of the mysteries of the universe.